Welcome to the Explainer. So we're always hearing about the next big AI model, right? But are they actually new, or are we just getting the same old engine with a shiny new coat of paint? Today, we're going to pop the hood and look at the actual blueprints to see what's really going on.
And you know, it's a totally fair question to ask. Because when you look at them, a model from today, it looks a heck of a lot like one from, say, 7 years ago. That basic transformer architecture? Yep, it's still the foundation for pretty much everything.
So yeah, that really is the core question, isn't it? Are we just polishing the same old thing? Well, let's find out. We're going to dive deep into those architectural blueprints and see what the developers have really been cooking up. And you'll see it's all about these subtle but incredibly powerful changes that are making today's models smarter, faster, and way more stable than ever before.
All right, first up, the quest for efficiency. And really, the first huge problem for developers is a pretty simple one. These models, they're absolutely enormous, and they're crazy expensive to run. So a whole wave of innovation isn't even about new tricks, it's just about tackling that massive cost.
So the problem is that a single AI model can have hundreds of billions of parameters, and that just eats up a mind-boggling amount of memory and energy. To get around this, developers came up with a really clever idea called mixture of experts. Think of it as a way to get all the brainpower of a huge model without, having to turn on the whole thing at once.
Okay, so here's the deal with mixture of experts, or MOE. The analogy is just perfect. Instead of having one single giant brain that knows a little bit about everything, you have a whole team of smaller, specialized experts. Then, when a task comes in, the model only calls up the few experts it actually needs, and makes the whole thing way lighter and so much faster.
And this comparison just lays it all out, doesn't it? On the left, you've got your standard, dense model. It's a total brute force approach. Every single parameter gets used for every single calculation. It's computationally heavy, it's a memory hog, the whole 9 yards. But on the right, the sparse MOE model is just smarter. A little router picks just a handful of expert parameters for each job. It's way more efficient, activating just a tiny fraction of the model's total size. So let's put some numbers on this. Take a model like DeepSeek V3. It has a total of, get this, 671 billion parameters. Just try to wrap your head around that. If this was a dense model, running it would be, computationally impossible for almost anyone.
But here's the magic. Thanks to that MOE architecture, it only activates 37 billion of them at any given time. So you get the vast knowledge of a 671 billion parameter model, but with the running cost of a much smaller one. That is a huge saving in both computation and energy. It's brilliant.
Okay, but MOE is only one part of the efficiency puzzle. There's another big bottleneck we need to talk about. The attention mechanism's infamous KV cache. Basically, this is the model's short-term memory, where it stores the context of a conversation. And boy, can it get bloated and slow things down in a hurry. So, the old way, multi-head attention, or MHA, was pretty inefficient. Every query head had its own unique key and value, which just ate up memory. The new standard is something called Grouped Query Attention, or GQA. It's a super clever fix where multiple query heads actually share the same keys and values. Think of it like a carpool for attention. Everyone gets where they need to go, but you're using way fewer resources to do it.
And some models, like Gemma 3, take yet another route. It's called sliding window attention. You can see the savings right here. Instead of full attention, which looks at everything all the time, this method dramatically cuts down on memory by just focusing on the most recent context, a little sliding window of text. It's another huge win for efficiency.
Okay, so making these models efficient is one thing. But what about just keeping them from completely blowing up during training? I'm not kidding, these training runs can take months and cost millions. Making sure they don't just fall apart is a true art form, the art of stability.
And this is where things get really interesting, because the changes are so subtle. Look at this. For years, the standard was pre-norm, like in GPT-2, where you put the normalization layer before the main blocks. It just helps keep the numbers in check. But now, newer approaches like post-norm put it after the blocks. And this tiny change has been found to dramatically improve training stability and reduce those dreaded loss spikes that can ruin a whole training run.
Here's another little trick of the trade, QK norm. All this is an extra little normalization layer, an RMS norm, that they stick right inside the attention mechanism itself. It's applied directly to the query and key vectors before they get compared.
It basically acts like a governor on an engine, just keeping the calculations from getting out of hand and ensuring the whole process stays smooth.
All right, so we've made models efficient and we made them stable. So what's next? Well, now we're getting to the really futuristic stuff, the radical ideas that could completely redefine AI architectures. We're talking about pushing future boundaries.
Okay, here's the big problem. The attention mechanism, as brilliant as it is, has a huge bottleneck. It's called the quadratic bottleneck. What it means is, as the text you feed it gets longer, the computation required to process it grows exponentially. Not linearly, exponentially. This is what stops us from, say, feeding a model an entire library of books at once.
So, to break this bottleneck, researchers are actually dusting off and perfecting an older idea called linear attention. It's a way to approximate the standard attention calculation, but it reduces the complexity from that scary quadratic growth down to simple linear growth. And that changes everything. It makes processing incredibly long sequences totally feasible.
And this isn't just a theory, it's already happening. Models like Q3 Next are using a really smart hybrid approach. They'll run, say, 3 of these efficient linear attention layers and then 1 full attention layer. It's a way to get the best of both worlds. Most of the efficiency of linear with the raw power of full attention when it's needed.
Here's another really wild idea that's gaining traction. It's called NOPE, which stands for No Positional Embeddings. Now, typically, you have to use this pretty complex system called ROPE to explicitly tell the model where each word is in a sentence. This is the first word, this is the fifth, and so on. NOPE just gets rid of it. The theory is that the model can figure out the order on its own, just from the structure of the attention. It's a really cool move towards a much simpler, more elegant architecture.
Okay, so let's circle all the way back to our original question. The verdict, evolution or repetition? We've looked at all these changes, making models more efficient, more stable, and even ideas that could totally change the game. So what's the answer? Are we just polishing an old design?
Well, looking at the key trends for 2025, the picture is pretty clear. Mixture of experts is becoming standard for big, efficient models. Attention itself is getting way smarter with things like GQA, and these tiny tweaks for stability are now absolutely critical. And on top of it all, the push for linear attention is a direct attack on one of the transformer's core limitations. So, yeah, while the main blueprint is still there, the actual components being plugged into it are fundamentally different.
The foundation is still recognizable for sure, but the engineering happening on top of it is undergoing a profound and really rapid evolution. We're seeing this massive shift away from just brute force scale towards really sophisticated, efficient, and stable engineering. It's not a revolution, but it is a very, very fast evolution. So no, the field is absolutely not stagnant. And that leaves us with one last big question to chew on. If Mixture of Experts solved the parameter count problem and linear attention is on its way to solving the context length problem, what's the next great architectural bottleneck that AI developers will have to smash through?